Let's begin by talking about what's in this unit here. So, you will have to explain qualitatively why an object moving at a constant speed in a circle is accelerating toward the center of the circle. Discuss the centrifugal effects with respect to Newton's laws. Draw free body diagrams of an object moving in uniform circular motion. Experiment to determine the mathematical relationship between period and frequency and one or more of the following. We're going to do them all. Derive an equation. Oh, so it actually says that you're supposed to derive an equation. I'll do it with you. I'll show you the way. Solve problems for an object moving with a constant speed in a circle using those ones there. Do you guys have problem types on the bottom?
No, there's an empty space.
There's an empty space. Okay, so apparently you don't have the numbers. Oh, it's on the back?
Oh, yeah.
Yeah? Okay, so there is horizontal motion, horizontal circular motion. There is vertical circular motion, and then there are banked and unbanked curves. You can take that to the bank. Talking about centripetal force. So, when you hear centripetal or centrifugal, what does that sort of mean to you? So from the center? Well, I should have had this already here with my. And is there a rubber stopper sitting on there on the computer with strings?
Rubber stopper.
You know what a rubber stopper is?
I don't think so. I'm actually doing good today.
So as I swing that above my head, it is accelerating. Now, if there's an acceleration, there has to be a net force, right? So if there's a net force, there must be a direction associated with that because force is a vector. So what is the direction of the force?
No, opposite rhythm.
What do you mean, Joel?
Like, it's, because you're pulling it, okay, so the string is like pulling this way, and you're pulling it that way, and it's already moving this way, so if you pull it this way, it's going to keep going.
Oh, so you're saying that the direction of the force is always changing because the direction that the stopper is at is always changing. Is there one way to describe the direction, even though I hear what you're saying, it's changing as it goes around, right? Which means? So it's towards the center? Or it's out, away from the center? Well, let me put it to you this way. Can you push on a string? Doesn't work, does it? You can only pull. So therefore the force is toward center or away from center? Toward center. It is centripetal. If you whirl a tin can on the end of a string, you find that you must keep pulling on the string. You pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. Centripetal means center-seeking or toward the center. The force that holds the occupant safely in the rotating car on the ride, like in figure 13.1, which we don't see here, is a center-directed force. Without it, the motion of the occupants would be along a straight line, and they would not revolve. Now, if you've been to the fair, you know, they got that, what do they call it? I always forget. You got the one, you walk in, it's in a big circle. Really? That's what they call it?
Yeah, there's like the other one that doesn't have the top on it.
Yeah, it's G-force.
It's open.
It's open, right? It just looks like a big salad collar, doesn't it, right? And then they got that little dinky little chain holding you in there, right? Is that doing anything, that little chain? Yeah. And then, oh, you gotta have it on, because that's safety, right? Yeah. Do you think that chain would hold you if you fell? No, it's like a little quarter-inch chain, right? Or sometimes they just use like a piece of shoelace or something like that. They might as well. right? And there's like you hang on, right? And then as you spin, what do you feel like? Well, you push to the outside. Push to the outside. Hold to the outside. But I thought this force, the text just said the force is towards the center. Well, what the heck is pulling you towards the center?
Well, it's not perfect. There's components of like there's two different parts of that force. One's going.
Well, it's a little hard to explain, but I want you to sort of keep that in mind here.
Something's got to be pulling it, so it's going to way.
Okay.
Is it something like something's in orbit? It's like you're getting pulled in towards, but you're going past it. And
Yeah, it's similar in a sense. Yeah, similar in a sense there, Dan. That's true. Let's read on here and then I'll explain. Centripetal means center seeking or toward the center. I read all this, right? Centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of a moving object and that tends to produce circular motion. Gravitational and electrical forces act across empty space as centripetal force, right? Like what holds the moon in orbit? Gravity force, right? It's towards the center of the Earth. Gravitational force directed toward the center of the Earth holds the moon in an almost circular orbit about the Earth. Electrons that revolve around the nucleus of the atom are held by an external force as it's directed toward the central nucleus. Centripetal force plays. I wonder where that highlight was supposed to be. Centripetal force plays the main role in the operation of a centrifuge. Familiar example is the spinning tub in an automatic washing machine. Who knows where the washing machine is in the house? I have to make that a little simpler. In the old days, I could say, who knows how to run the washing machine, but I can't say that. Who knows how to run the washing machine? Oh, excellent. Well done. You know, a little tub inside, what does it do? Just a little shot. What does it do? It spins to do what, Shelby? Does it spin to wash the clothes? Yeah, it gets rid of the water, right? It sort of pre-dries them for you, right? Oh yeah, they're still pretty wet, right? But you'd be surprised how much water is actually, right? In its spin cycle, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes, which are forced into a circular path. The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water in the clothes. The water therefore escapes. It's important to note that a force acts on the clothes, not the water, right? So the clothes are being pushed in towards the center, but the water can't because of the holes, right? Same idea with the salad spinner at home, right, in the kitchen. No force causes the water to fly out. What causes the water to fly out then? Inertia. The water will do that anyway as it tends to move by inertia in a straight line path, unless acted upon by a centripetal or any other force, right? Objects in motion stay in motion. So the water, as the tub is spinning, right, the water's going out. It's going out in the same path that it was forced to, and the clothes are being pushed in. So interestingly enough, the clothes are forced away from the water, not the other way around. Who cares as long as they're a little bit drier? When an automobile rounds a corner, the sideways friction force between the tires and the road provides the centripetal force that holds the car in a curved path. If the force of friction is not great enough, like on an icy day, the car fails to make the curve and the tires slide sideways. The car skids. So as you're making a left turn, it's a weird thing to think about, right? You're making that left turn, and in fact, what's happening is friction is actually pushing you to the left, right? Your car is trying to go like this, out, but friction between the tires and the road is actually pushing you towards the center of your curvature radius, which is why we bank curves, which we'll talk about in a week or so. Okay, does that sort of kind of make sense? So, centripetal and centrifugal forces. In the preceding examples, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to circular motion. This outward force is called centrifugal force. Okay, so two different words, centripetal and now centrifugal. This outward force is called centrifugal force. Centrifugal means center fleeing or away from the center. In the case of the whirling can, it's a common misconception to state that a centrifugal force pulls outward on the can. Not true. Right? Where's the force on the can, the rubber stopper? Which direction? In, towards the center. Centripetal force. Centrifugal force is outward. Which is being forced outward? String. The string is being pulled outward by the mass of the stopper. If the string holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from its circular path. But the fact is that when the string breaks, the can goes off in a tangent straight line path because no force acts on it. We'll illustrate this further with other examples. So just as Carter said, when I let go, where should I let go, Carter? I almost did. Sorry, man. Should have practiced. No, it's not okay. Oh, probably that's enough. Look at that. I was really aiming. I was aiming for over there. I should have made sure you were looking. How come the rubber stopper flies? It's not because of the force. It's because there's no more force. Objects in motion stay in motion. So when I let it go right there, right? I should have let it go right there. Right? So it was headed that way. Exactly. Suppose you're in the passenger of a car that suddenly stops short. You pitch forward against the dashboard. When this happens, you don't say that something forced you forward. You know that you pitched forward because of the absence of a force which a seatbelt would have provided. Similarly, if you're in a car that rounds a sharp corner to the left, you tend to pitch outward to the right, not because of some outward or centrifugal force, but because there is no centripetal force holding you in a circular motion, as a seatbelt provides. The idea that a centrifugal force bangs you against the car door is a misconception. So when you swing a tin can on a circular path, there is no force pulling the can over. Only the pull by the string acts on the can and pulls the can outward. The outward force is on the string, not the can. The outward force is on the string, not the can. Okay, now let's complicate the matters even more by putting a ladybug inside the whirling can. Or a person inside the, what was it? G-force? Okay, because that's really the same thing, right? Suppose there's a ladybug inside the whirling can. The can presses against the bug's feet and provides the centripetal force that holds it in a circular path. The ladybug, in turn, presses against the floor of the can. But, neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, we see that there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but to inertia, the tendency of a moving body to follow a straight line path. Try telling that to the ladybug. Or the person inside the G-force, because when you're in it, you feel what? Sick, probably, yeah. Heavy, right? You're thrown up against the wall, right? You feel that gravitational pull, but there is no centrifugal force on you. There is a centripetal force keeping you in that circle, right? But it's inertia that's forcing you against the wall. So it's kind of a weird thing. And it depends on your frame of reference. If you're outside it and inside it, they're two different things. Go ahead, Alana.
Explain that like astronaut thing where they spin around real quick and experience that like high G-force?
Yeah, well, I mean, it's the same idea, right? They spin them around really fast to get them used to G-forces. They also check to see how fast they black out. When pilots go into when pilots go into a dive and there's that they're either going down or up, right? Depending on which way they're going, all the blood can rush away from their head, which will cause them to black out. And they actually wear suits. The pants will actually compress as the plane experiences that. Their pants will compress and it forces the blood back up to their head so that they don't black out. Yeah, because that's a bad thing to black out while you're piloting the plane at high speed. Yeah. Yeah. Okay. You want me to explain that?
No.
Okay. Centrifugal force in a rotating reference frame. Our view of nature is very much influenced by the frame of reference from which we view it. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. So when you're sitting in the train, you're cruising down the rails, right? You can walk and you can have a drink and eat your lunch and do whatever, right? Because your speed relative to the plane or to the train is zero. Everything's moving at that speed, right? But Joel out there on the side of the road, the little kid waving at the train as it goes by, well, he sees you, your lunch, your chocolate milk, everything going by at 8 kilometers an hour. So the frame of reference is important. We have just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centripetal force. For the ladybug, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. But nature seen from the reference frame of the rotating system is different. In the rotating frame, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. Centrifugal force in a rotating reference frame is a force in its own right as real as the pull of gravity. So for the ladybug in the can, they feel the force. For the person inside the G-force, they feel it, right? For the astronaut inside the big rotate, have you ever seen the TV series, I think it's called The 100? It's like, have you seen that? Yeah? It's like a sci-fi thing that there's like nuclear Armageddon on Earth, and they put a bunch of humans up on this big ship called the Ark, and then they send 100 kids down there to see if it's okay, and then chaos ensues. I don't know why they said teenagers.
Well, they were all friends.
Oh, was that right?
Well, I have the books.
Oh, maybe, yeah. I think you're right. I only watched the first of it. Anyways, they're walking around this space shuttle, no problem, just like it's you and me walking down the halls, right? How do they do that? Yes, they have to have it actually has to be rotating, and it creates a sort of simulated gravity. Now, it's not near as, you can't do it quite that way. There's a really interesting clip that I always think about when I teach this. I've yet to find it on YouTube. It's an old movie. It was made in 1968 or 67, something like that, called 2001: A Space Odyssey. And the guy, have you seen that one? You read the book? Yeah. Okay. Right, but he's actually running. He's in a giant rotating thing, and he's running up the walls like this and going all the way around. It's a really cool piece of film, actually, especially from the late 1960s. Because it's not CGI. I'm not quite sure how they did it. But that's what I think about when I do this, right? So you can simulate gravity by performing this circular motion thing. Okay. Nature seen from the reference frame of the rotating system is different. In the rotating frame, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. Centrifugal force in a rotating, I read this already, right? In a rotating reference frame is a force in its own right, as real as the pull of gravity. However, there is a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity we experience is our interaction with the Earth. But centrifugal force in the rotating reference frame is not part of an interaction. It is like gravity with nothing pulling. Nothing produces it. It is the result of rotation. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and the nuclear force. So you remember back in grade 11, there was the 4 fundamental forces, and some of you I realize may not have seen those. The 4 fundamental forces are gravity, electromagnetic forces, and the weak and strong nuclear forces. This one is not one of them. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Just as from the surface of the Earth, we find gravity ever present, so within a rotating system, centrifugal force is ever present. And so the idea is that in the future, hopefully, when we're building those arcs or whatever they are, right, that they will use this rotating thing to create a sort of simulated gravity. But for now, they just have to float around with it. Okay, so I got 2 questions for you. I think you have them there, right? And you have to do a little bit of sort of mental thinking there, or visualizing. A heavy iron ball is attached by a spring to a rotating platform as shown in the sketch. Okay, so I've got a ball here and it's on a spring. And this merry-go-round is going to be spinning around. 2 observers, one in the rotating frame and one on the ground at rest, observe its motion. Which observer sees the ball being pulled outward, stretching the spring, and which one sees the spring pulling the ball in a circle? So they've got a male in the center, and a female is outside. So which one sees the ball being pulled outward, stretching the spring? Which one, the man or the woman, sees the ball being pulled outward, stretching the spring, and which one sees the spring pulling the ball in a circle? The centripetal?
Yeah.
Shelby thinks the woman sees the centripetal, which is which one? The spring pulling the ball in a circle or the ball pulling over? The second one. This one here is the centripetal, and the first one is the centrifugal. Centrifugal. Here's the answers right here. Oh, well, that's no good. I'm going to have to rotate the whole thing. Because I don't trust my explanation. Trying to do this. And not being very successful.
No.
Yeah, I'm trying. It's been so long. I can't teach anymore.
No. You can do this. Mushroom.
Shelby's such a defeatist.
Ooh, it's a big word.
It is. The observer in the reference frame. Do you guys have the answers on the bottom? Oh, you do. How many people thought to turn over and look at it? Don't answer that. The observer in the reference frame on the rotating platform, that's the man, the male, states that a centrifugal force pulls radially outward on the ball, which stretches the spring. The observer in the rest frame, that's the woman, the female, states that a centripetal force supplied by the stretch spring pulls the ball into a circle along with the rotating platform. So, were you right or were you wrong? You were right. The rest frame observer, the woman, can state in addition that the reaction to this centripetal force is the ball pulling outward on the spring. The rotating observer, interestingly enough, can state no reaction counterpart to the centrifugal force. So that whole action-reaction, you know, Newton, if Newton was in a rotating reference frame, Newton would not have come up with that. It doesn't make sense. There is no reaction force, interestingly enough. So Newton's laws do not apply to rotating reference systems, which interestingly enough is the Earth is a rotating reference frame. But yeah. Okay, now hopefully you didn't read the, did you read the second part?
Yeah.
Did you read the second answer? Don't read the second answer. Let's try the question. Joel, put the phone away here. What's the second question? The spring in the scale in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis and the outer edge of the circle of power. I got to rotate this upside down again. Give me a second here so I can explain. Okay. The spring in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis and the outer edge of the circle power. So if you put the ball there, then the spring will stretch 10 centimeters. Okay? If the spring support is moved so the ball is directly over the edge. So now instead of the man sitting here, now we're going to take that whole thing and we're going to move that blue post about there, which moves the black post, or moves the ball about there, right? Just to the edge. So you understand what I'm saying? Is that it's not attached in the middle anymore. Okay? If the spring support is moved so the ball is directly over the edge, will the spring be stretched more than, less than, or the same 10 centimeters?
What do you mean?
Will it stretch more than 10 centimeters because it's placed further out?
Oh, it's the same. It's just go over.
That's the same? It'll just go over the edge, right? Who's been on a merry-go-round as a kid? Everyone. Where is it moving the fastest?
Oh, is that whole plate moving?
No, just the center. It's rotating.
The whole thing?
The whole thing.
Not just the tube?
No, not just the tube.
I thought the guy was spinning, holding
It's a merry-go-round. No.
Oh,
Right.
never mind, yeah.
Good change? Where is the merry-go-round moving the fastest? Outside. The farther out you get, the faster it's moving, right? How come? Because you got to go way farther in exactly the same amount of time, right? If you're feeling sick, where do you go on the merry-go-round? Into the center, or get off, I guess, right? If you want to go really fast, what do? You hang way out on the edge. We all did that. So is it going to stretch more, or is it going to stretch less? More. Turn it upside down. The ball will have twice the linear speed at twice the distance from the rotational axis. The greater the speed, the greater will be the centripetal force, which will also be twice and stretch the spring 20 centimeters.
Interesting.
Okay, now, who doesn't love a helium balloon? Who doesn't love balloons, in fact? Now, what would happen if you were to take a helium balloon? So just treat this as sort of part of this intro learning here. Don't worry too much about the mark or anything. So these are based on that reading that we just did. So you're spinning a bucket attached. Let me just start the question here. You are spinning a bucket attached to a string in a circle over your head. What kind of force holds the stopper? It should be a bucket, I guess, right? In a circular path. Yeah, I can't change that. So what is holding the object in that circular path? Is it A, centripetal force, B, centrifugal force, or I guess if you want to answer C, you don't know, then that's telling me something too. You don't know which one. You are spinning a bucket attached to a string in a circle over your head. What kind of force holds the stopper in a circular path? Is it centripetal or centrifugal? Apparently I have to go through all the questions, right? Yeah, that's okay. We'll do it that way. Blair, shall we? Oh. In a washing machine, during the spin cycle, the force is on the what? Causing the water to be separated from the clothes. The force is on the water or the force is on the clothes? Carter, put the phone away and pay attention here. The force is on the water or the clothes? A tube has been placed upon a table and shaped into a three-quarter circle. A golf ball is pushed into the tube at one end at high speed. The ball rolls through the tube and exits at the opposite end. Describe the path of the golf ball as it exits the tube. So it's being pushed in here, and it's flying around. So when it comes out, will it go to A, will it go to B, or will it go to C? A, B, or C. Which direction will the golf ball go? Yep. The table is like this. It is flat, but you're looking at it sideways. No, it's like vertical. It's vertical. Vertical.
No, like,
Flat on the table.
B, like in line with the table.
Yes.
So that you can't come off with that. I thought it was like
Sitting like this. I haven't been here for a while. I forgot it's school.
What do you mean? I forgot about school. You should be an artist.
I should be an artist?
Architecture. Or carpenter.
I think I do pretty good what I do.
Okay, just like a job.
Oh. Mr. Bennett or someone else is spinning a rubber stopper at a constant rate of 3 revolutions per second. The rubber stopper is accelerating. Mr. Bennett's still spinning the rubber stopper. What direction is the force on the stopper? In, out, or tangent to the circle?
Oh.
A, B, C, tangent to the circle. When you're driving your car and you make a left turn, friction between your tires and the road causes the car to move to the left.
Finish.
Yeah?
Yeah.
Says your name still here, Shelby.
Well, it's gone. That's awkward.
There we go. Okay. That's it?
It's gone. Oh.
How'd we do? 89% as a class. Starting the new year off right.
How is
Okay, so the correct answer here is a centripetal.
See? Another
Centripetal.
only if you get them.
Which one is it here? It's on the close. The force is on the close, not the water. Here, which way is it going to go? B flat. The velocity is tangent to the circle. So the velocity is tangent. Right? So it's, yeah, it's just going to go straight out like that. True. Accelerating. Which direction? Towards center. And what direction is the force on the stopper? A, in. Yeah, I think I told them all to you, really. And did I say this one? Sure did. Yay, everyone got it. True. Okay, awesome. Okay, I'm done the talking part here. I'm going to hand out a little reading. But first, they were looking for you in the office. That's it.
Here you go.
Oh, yeah? Personal coefficient? Oh. Is that right? Sir?
Yeah, I like all this.
Yeah, there is.